Okay, I'll now be implementing segment tree live. So to implement a segment tree, first we need to create a structure. This structure will contain a node of our segment tree. So each node will store the start value, end value. Each node will store the start value, end value, its midpoint, as well as the minimum value of all the leaves within its subtree. So to create a node with a value of s and e, we first set its s value and its e value. Now the m will be s plus e over 2, which is halfway into the node. And then now we need to consider the value of v. Initially v is equals to 0, so let's just set it to that. Now let's say that we want to update the node p to value of u. If s is equals to e, that means it's a leaf, so we can simply set the value of v to be equals to u. Now if p is less than or equals to m, that means that it's in the left child. Wait, speaking of left child, we need to create children. So here, if s is not equals to e, then we need to create two children. Because this will allow us to get the recursive tree-like structure. So when we update, if s is equals to e, then we set v to be equals to u, because that means that the current node is a leaf. So we can simply update the value of the leaf. If p is less than or equals to m, that means that we are at the left node, that p is within the left node, so we need to update the value of the left node. However, if p is greater than m, then that means it's in the right node, so we will update the value in the right node. After that, we need to recalculate this v, which is the value inside the current node. So we will recalculate it as the minimum of the values in the left and right node. Now we need to query the range L to R. If S is L and E is R, this means that we are querying the entire node. So we just return the minimum value inside, which is V. Now if R is less than or equals to M, then that means that we are querying entirely in the left node. So we will return the query within the left node. Since we use L and R for the left node, we should probably use X and Y for our query though. Now if X is greater than M, you return R query X, Y, because the range X to Y is entirely in the right node. Lastly, if it crosses between, then we shall query both the parts in the left node, which is X to M, and the part in the right node, which is M plus 1 to Y. And then if we take the minimum of both parts, it will be the answer for querying X to Y. Now we also need to create pointers to the left and right node, which will basically point to the places where the memory is stored. So this allows us to access the left and right node. Now we will create a pointer to the root node, which we'll create later. Now let's process all the queries. So this segment tree goes from 0 to n minus 1 because it's 0 index. So we will create the node from 0 to n minus 1, which is a range of indices. So now we will process all the queries. Now if it's a type 1 query, which is here, it's an update. So now we just update the root node by using the update function. But if it is a query, then we just use this query function with A and B. So we just do this, and now we test. Wait. Okay, we need to input A and B here as well. Wait. Wait, sorry. Wait. Wait. Hold on a second. Okay, anyways, here when you update, if it's a leave node, then you do not want to continue to recurse any further. So you should just stop there. And then now we can submit. Okay, I'll now be moving on to Fenwick trees. So first you can look at segment tree 2, which looks like a regular segment tree, but it turns out that segment trees use a lot of memory. So if you just try to implement a regular segment tree for segment tree 2, which is a problem where there are 10 to the power of 9 nodes, then your MLE. But before we continue talking about Fenwick trees, does anyone have any questions about the implementation for segment tree, which will be shown here? If you have any questions, please ask now before we continue talking about Fenwick trees. Okay, I'll assume that we have no questions then. So I'll now move on to Fenwick trees. So Fenwick tree is where there is no explicit linkage between nodes. So this means that unlike in a segment tree, where as you can see we had a pointer from a node to its children, there is no pointer stored between each node and between a node and its children. So instead it's just stored in an array, and then we do some math to calculate the value of elements and perform updates. And similarly, as a segment tree, you store the sum of ranges covered by its children for each node. So for a Fenwick tree, only n nodes are used for the entire tree to cover an array of size n, whereas for segment tree you need 2n minus 1 nodes. Also for Fenwick, the range of its children are asymmetrical, so you cannot just flip it and get the same structure. So we'll now talk about how to construct it. So let's first consider this operation, which is the least significant set bit. So it finds the smallest power of 2 that divides an index. For example, the least significant bit of 4 is 4, because 4 divides 4, but 8 does not divide 4. As you can see, you can calculate it using bitwise n. So here is 0, 1, 0, 0 and 1, 1, 0, 0, which is 0, 1, 0, 0. Similarly, the least significant bit of 3 is 1, because 1 is a factor of 3, but 2 is not a factor of 3. Okay, so if we have an array of values which we want to construct a Fenwick tree on, we'll construct another array f. So each element contains the sum of elements in this range, which is from I to ls from I minus the least significant bit of I, with a rounded exclusive of I minus ls bi, up to I inclusive of I. And the elements of f contain the sum of elements in the ranges covered by their children, so it's a bit like a segment tree. So we will need these 3 trees in order to perform operations on the Fenwick tree. This one is not used very often, but we'll need the interrogation tree and the update tree. So for the interrogation tree, the parent of a node is I minus LSB of I, or in other words, I and I minus 1. For example, the parent of node 6 is node 4, which you can think of it as toggling the least significant bit. So you can also consider node 0 to be the root node, so you start iterating from here. So to find the prefix sum for AI, we just sum the values of fi is parent, parent's parent, and so on. For example, for node 6, the f of 6 is equals to the sum of values in node 5 and node 6. Then after that, you traverse from node 6 to node 4 is parent. The values of A stored in node 4 is A0, is A1, A2, A3, and A4. So if you sum them up, you get the sum of A1 to A6. And to find a range sum, you do the same thing as regular prefix sum. So now we'll consider update tree, which is how you update nodes. So the parent of node I will then be I plus LSB of I, which is unlike the interrogation tree where it's I minus LSB of I. For example, parents of node 4 and node 6 are node 8. So to change the value AI, you first calculate the difference between the new value and the original value. And then so you increase this change to fi, and then you also do the increase to f of the parent of I, and so on. For example, to update node 6, for example, to update the value of A6 by 1, you first increase node 6 by 1, because the range for 6 covers node 6. Then you increase node 8, the value for node 8 by 1, the f value for node 8 by 1, because the range of node 8 covers node 6. And after that, you increase the range for node 16 and so on until the index exceeds the value of n. So there's also this search tree which is not very useful, where each node is assigned a height based on the number of trailing zeros in its binary representation. So for example, the odd indices are leaves because they comprise of exactly one node. And then the children of a non-leaf node are these indices, are the nodes with these indices, and this is for the parent of a node. However, this tree isn't really used often and you probably don't really need to know it. So for implementation, like a segment tree, we need a few details. Like firstly, we need the type of the data type, and we also need the data type of the range. And then after that, we need a combiner function. For example, normally it will be the sum of numbers if we want to calculate the sum of a range. We also need an LSB function and an original value array of values. So we don't need any structures, all we need is a few arrays for Fenwick tree. So essentially we construct the Fenwick array by using this formula over here, and then we can do it naively, which is O of n log n. And then for query, we store a sum which we initially set to 0 because the sum of 0 elements is 0. And then for each parent of the original index, we add the f value of the parent. And then after that, we proceed to go to the next higher parent. And once we're done, the sum over all parents will be the value that we get. For update, we do the same thing, but we transverse the update tree instead. So for each parent in the update tree, we increment it by the change in value that we want, and then after that we go up to the next parent. So now we can implement the problem Fenwick tree. I guess I'll pause here and give some time for you to do so. Before I start though, before you implement it, if you have any problems regarding Fenwick tree, please ask them right now. You can do so either in the live chat or the Discord. In the meantime, if you have no other questions, you can start doing the problem Fenwick tree, where you have to calculate the range sum, and also in the meantime you can probably do subtask 1 of Fenwick tree, where you update a point value and also you do a range query. For subtask because for subtask 1 the update is a point update.
For second Fenwick tree, do we need like a difference array or